So, thank you for inviting me to give this talk. So I'll mention this is a project from my academic group. So it involves my students, Jack, Isa, Schuler, Yash, and Condi. Megan.
Yash is Condi.
Yes, Megan. And it also involves a collaboration with Muthu and Karmit. And they are from their company, Lahero. Okay, so the goal of this is threshold factoring from factoring. So we'd like to create an RSA modulus n. And the only assumptions we'd like to use are factoring assumptions. And let's say symmetric primitives like SHA-R256. That's kind of a doctrinal question that's driving this, but we're not really tied to it. The main reason I want to phrase it that way is that we are trying to see how well we can do with this approach without using something like LWE. So there are some nice approaches with even just additive homomorphic encryption that will substantially improve one factor of this construction, but at the cost of some other factor. So in particular for this application, it's not clear that if you want to use a VDF for consensus, that you want this sort of assumptional pollution. You want extra assumptions that make their way in there, and that then you have to make analysis about what LWE parameters are, et cetera. So this is how good can we do just using sort of factoring assumptions. The other caveat is that we would like to achieve n-1 security. And this is again for the application, but also it handles, for example, questions like Joseph's question about Sybil attacks. Muthu made the nice point, which is that when you have n-1 security, all you really sort of need is one honest participant. So even if there are a bunch of Sybils that are controlling several accounts and so forth, as long as you have one honest participant, then the privacy of the computation is secure. And of course, Diogenes spent the whole lifetime looking for that one honest participant. And certainly they didn't look in any Ethereum forum and find them there. So it's not clear if you could find an honest person, but but we can hope. This talk is going to discuss the semi-honest version of this construction. I'm just going to highlight. This is a work in progress. I thought we'd have a better paper at this point. We don't have a paper we can post to ePrint, and our implementation is like modular but not glued together yet. So this is a semi-honest argument for what we're planning to do and what the performance of our semi-honest approach is working. But our target is, of course, malicious. So the part that I'm not going to talk about is how every choice that we've kind of made here really helps us build a malicious version of this protocol with very little overhead. So other approaches have basically used zero knowledge as sort of a heavy hammer, and that requires a pretty large zero knowledge statement about what you're doing. What we're planning to do is actually it's surgical, as I'd like to think, and builds on our work from our ECDSA. We have a nice way of getting malicious security for multipliers in that case. So what are the big wins? So here's really how we improve over this. I'll present some of the prior work, but at the high level, we're using more efficient primitives, in particular the multiplier, and that in combination with this other observation, that allows us to have fewer candidate trials. So when you're producing RSA, just like when you do on your SSH keygen, your computer is basically picking a random number and testing whether it's prime, doing it again, multiplying, and then producing that result. So this process inherently requires sampling. So we have to do a bunch of candidates, and then we have to try and check if they work. And when you do them in the plain text, like SSH keygen, none of these things that we're doing make sense. But when you're thinking about a secure computation for the same thing, actually using a different algorithm for the same process is generally always wins when it's something like this that has a lot of algebraic structure. So we have some observations that allow far fewer candidate trials. And finally, we're basically attempting to achieve less communication per trial. So the three of those things are basically what get us improvements over what the status quo work is. And the major idea come from two basic, very simple observations, which nobody seems to have used, but we are using them aggressively. The first is the Chinese remainder theorem. So for our multiplier, we use the Chinese remainder theorem. I'll show you exactly how that works, but it gives you a pretty good factor improvement. Even our own ECDSA, we had a threshold ECDSA a series of works there. We didn't use this observation, and that immediately gives you a factor 4 improvement in communication, which is quite big. So now, given that the moduli are those are 256-bit moduli, now that the moduli are are 1,000 bits, 2,000 bits, then this thing gives you like a factor of 16. The second thing is more constructive. So you can look at sieving as one way or the other. You can either looking at it as building up a candidate that satisfies all of your constraints, or you can look at it as sort of like the way politics are. You put something out there and everybody tries to tear it down. And so we're trying to be constructive in our approach, and it turns out that that actually helps. And I'll explain that sort of later on. But that's the high-level idea if you want to keep that around as we go through this. So this is a very popular topic, starting from Benét Franklin and Frankel. I forget the M, but the Y is Young. Starting from the right around the late 90s, a lot of work basically on how to do this. These last few right here, they are actually closer to implementable. In fact, this one and this one both have implementations of their approaches. And so again, we're making quite a bit of progress. I will basically start from, what I want to do is start from this right here, the Benét Franklin approach. They lay out a protocol for doing this, and it's kind of the protocol that everybody's kind of building upon, and there are a few different ideas, but this is the basic idea. The protocol is in sort of 3 phases. We're going to sieve, do some sort of sieving, and different people use different approaches for that, in order to get some candidate P and a candidate Q. We're going to multiply. So that sieving can be very generic. In fact, you don't have to you can just pick a random P. That could be null sieving, but you can do some sort of trial divisions to sort of speed things up. Then you're going to multiply them. Again, this is a secure computation, so at the end of this we'll have shares of n, and then we'll finally reconstruct n. And finally, we'll do some biprimality testing right here. We'll run this n through sort of some tests using like this notation right here, bracket P and bracket Q means shares. So all of the participants of the protocol have shares of P and shares of Q. They'll use their shares of P and shares of Q in order to test the biprimality of n, and that test results in a 0 or 1. And if it's a 1, then it's a good candidate. So that's the approach we take. We build on this approach, and many of the implementations all build on this type of approach. But just to be sure, I wanted to highlight some of the other approaches that might be floating around your head. Why can't we do it this way? Why can't we do it that way? What's wrong with this approach? So for example, Damgaard Mikkelsen, they of course also follow this same kind of approach here. They're going to create a few candidates. They're going to do some primality tests, and then they're going to what I didn't mention here at the end here is basically ZK proof, to basically prove that the result, once you have a really good result, a good n, then you can basically prove that the run of that instantiation was correct. And if you do the right commitments, if you commit your inputs ahead of time, then this approach is the best way to get malicious security, in our opinion. So it's again the same sort of rough sketch. The observation they make, which is a very interesting one, and if we can, this is an open challenge. I like the approach that the previous speaker did about, here's a challenge. If we can get something like this to work, then we can get a factor of Lufrey 20 improvement over what we have. So generally we have some shares of P and some shares of Q, and we multiply them to get PQ, and we can do biprimality when we have this type of thing. But of course, when you do this on the plain text, what you actually do is some sort of Rabin-Miller test on this P. And so why can't we do that in a secure computation? In fact, that's a question that was answered by the ACS paper, Kamenisch and Schuper, the CNS, forgotten the A. Alzheimer, yes. And DM10 is an improvement of that approach. And here's the reason why that's tough, is because this Rabin-Miller requires you to do a computation of this form, a to the p minus 1 mod p. And the thing is, p is basically in a sort of shared state. So ACS was basically proposing using a circuit. And in fact, one of our very first papers on malicious two-party secure computation, we basically implemented modular exponentiation, this type of thing. And it's billions and billions of gates if you do it using just Boolean circuits. So you have to do something better if you need to do this, because this is something you have to do several times and so forth. Once, maybe you could do it 3,000 times. It's not so clear. So they had a very nice observation on how you can do this type of thing using an approximate base. Right. No. This is It's Boolean circuits are super fast now. Like in 2011, we took like maybe an hour or two or something like that. So today they're much. I mean, it's faster. So it could be done in tens of minutes maybe. But the point is, we have to do this Rabin test several thousand times in parallel. So I mean, the parallelism helps, but
not just that. It's multi-party. Like I mean,
yeah,
regardless
right.
of the two-party, the multi-party you have to do like VMR doubling, which is also
Right. I mean, actually, like XKR is the best approach to that. Like we could actually do something like this. This would be a brute force approach, but I'm going to argue it's dominated by what we're doing, and you'll see it's dominated by this particular approach is also dominated. So the whole approach was how to try to test P by itself and then Q by itself and then combine a P and a Q. And they had a very nice approach using this like you can basically do modular reductions mod P with some approximate. You could do an approximation that gets you into a factor of plus or minus 4 times P, okay? And so if you're familiar with the paper, this will make sense, but it gets you an approximate version of what this number is, and so you only have to check, let's say, roughly 16 possibilities, okay? So that's a great improvement, but it's still a degree 16 polynomial that you need to evaluate as an arithmetic circuit, okay? So essentially, one test requires roughly 16 multiplications, multi-party multiplications to compute. And you have to run that one test when you do the Rabin-Miller test with a very nice, clean analysis by Demgaard and a previous author. They show that just one test basically shows that if it passes, then it's prime with, in the average case, for the size of primes that we care about, it's prime with probability 2 to the minus 38. Which is awesome. You don't have to do a repetition of something like the Binet-Franklin test. So the thing is, to get to like the security parameter that we need, you kind of have to repeat it like twice or 3 times. And so still, you get into several multiplications just to check one P. And you'll see that, so already if you do the math, remember the number 16 times 3 is roughly 48 to check one P. Then you have to check another Q right there. So that's kind of like 96 multiplications. Keep that number in mind, 96. We're going to have a number lower than that for our approach, and you'll see why this is dominated currently. So that's not to say this is what when very enthusiastic number theory, like math students come into my office and ask for some problems, I tell them to read this paper, and I say there's room here. Probably you can like whittle these things down. If you can get it down to like from 4 possibilities, plus or minus 4, to like maybe 2 or 3, if you have a tighter analysis, this might become a winner. So, so there's approach here. I'm putting it out as a possible approach. Currently, as it's stated, we've taken a different one for these calculations.
So for the background you said you have to repeat it twice?
No. So in your prime, we have.
But that's only because the same is true for the Miller-Rabin test.
So they do an analysis. The specific test they do with the other tests, they show that on average. Right, so you're right. Maybe what you're saying is on average it could be something similar.
Same would apply to the BF test.
It doesn't, because so in their particular analysis they require this divisibility property of p minus 1 not being divisible. So they require they have a specific divisibility criteria, and they specifically point out it doesn't work for biprimality tests.
I don't believe that.
You don't? Okay.
You should be able to get
Okay. Yeah, so it's like p minus 1 is yeah. I'll follow up with you with the exact claim they make. I haven't verified. I've just taken their word for it. So yeah, that would certainly help us. Okay. So Hazai et al., they have another approach to this, and I just want to outline it. So what they are basically exploiting is additive homomorphic encryption. They're really taking that and sort of and getting great multiplications. As a result, they require, in their implementation, they require the Paillet assumption. So this is kind of doctrinally different than ours. You need to make a stronger assumption to get this. Also, Paillet is not especially efficient. So in one particular, so the way their protocol works is before, these are the 3 basic steps, right? They have to do this key setup, this distributed key setup. So they use Paillet as well as El-Gamal. Let's put that down there as well. So they have to do a distributed key setup. That's kind of, it's like a messy thing. Of course, it's currently feasible if it was like, if this was definitely a winning approach, this could be this could be overcome. But
So if you have a Payeki, you already have an RSA modulus.
so they're using essentially everybody creates their own Payeki, and then they kind of, it's like threshold oh, sorry, not threshold. It's like everybody creates their own, and they do pairwise. So basically, to do multiplications, they are using this additive homomorphism. So if we have P and Q, you know, A plus B times A1 plus A2 times B1 plus B2, I can basically encrypt my share, give it to you. You can raise it and do some summations, and that could basically work out. That's what they do, I guess that's all I really need to say, is that they're using Pi to do multipliers, and they also have a very careful malicious security argument based on having El Gamal ciphertext that sort of parallel, that run in parallel to the entire computation, and then they prove equality between these two. So I just wanted to put it out there. I think LWE will now be a better mechanism for this, so it'll be dominated by whatever approach uses LWE. But as I said in slide 2, I basically put that concern aside. So, yeah. So finally, this is the latest approach. This was from last year, and this is what sort of initiated our look into this. This is FLOP, and they basically do, again, they do exactly the same. You can look through their protocol and now basically parse it into these basic into basic blocks, like so generation, construction, division, and primality testing. And their big observation is to go back to a paper by Gilboa in the late 90s, who also considered the problem of threshold of RSA generation. And he created an integer multiplier from basic OT building blocks. So here is what the primitive is. You have an A and a B, and you want to multiply. So one party has A, one party has B. You want to multiply them and share results so that essentially the two parties have additive shares of the product. That's the building block. And what Gilboa is going to do is to build this out of 1 out of 2 OT. So remember oblivious transfer, essentially one party basically has 2 inputs here, the other party has a single bit right here, and essentially if I put 0, I get the 0 input. If I put 1 as my input, I get 1 as the input, and the standard security properties, you only get 1, and the other party doesn't know which one you picked. So with something like this, the way you can build a multiplier is you can basically have one of the parties here basically put either Ri or B plus Ri. And this Ri is basically a different Ri every time. So that would be R1, this is R2, B plus R2. This would be like RL and B plus RL. So that's what one party puts as the inputs to the OT. And the other party just uses they take their input and break it down into a bit decomposition and just use each bit as the input to the OT. Okay? So the output we're going to get from this OT, let's call that S1, S2, all the way up to SL. Didn't I do that? Did I? We're good? Okay. So oblivious transfer. This is a 2-party protocol. One party basically has 2 inputs, a 0 input and a 1 input. And they put strings there. They can put whatever they want there. And then the other party just has a single bit input. It's a 0 or a 1 here. And essentially, the receiver party, they get basically, they get essentially, if their input was 0, they get the 0 input. If their input was 1, they get the 1 input. And the sender doesn't know which input the receiver got. And the receiver only gets 1 input. Okay. It's a multiplexer, yes, exactly. Secure multiplexer. Okay. So, so what I want to say here is that what's very cool is if we run it like this, essentially this party is going to basically take Ri times 2 to the I. That's going to be their share. So this is going to equal C2. And C1 is just going to be the sum of Si times 2 to the I. So this is basically the multiplier. You run L copies of 1 out of 2 OT with these as inputs and these as outputs. And these are your basic shares. To see why that basically works, so imagine, so I have A here. And if my AI was 0, then I'm basically going to get Ri. And if my my AI is 1, then I'm basically going to get B plus Ri. So this is what Si is equal to. So if I take the sum here of Si times 2 to the I and just break that out, you basically see that so in the case that AI is 0, then I basically just get these Ri times 2 to the I terms. And when it's 1, I basically get, right here, I basically get AI times Bi plus Ri plus Ri times 2 to the I. Okay? So over here, basically, when you sum all of this up, this party basically gets A times B plus Ri times 2 to the I for all I. In the 0 case, you get this term. In the 1 case, you get this other term. And over here, remember, this person's share was basically Ri times 2 to the I. So when you add them, essentially, these two terms cancel out, and the product is AB. Does that make sense? Okay? So the one, and this is the critical point here, why the CRT helps. So to do a k-bit multiply, so we are I'm saying that A is in 2 to the k here, but we can work in bigger rings. That's fine, and we can work in such a large ring that the inputs won't wrap around. So the important point is that if the inputs are k bits, then we have to do k OTs, okay? And of course, we're not going to use oblivious transfer. We're just going to use this other very clever primitive called oblivious transfer extension, which allows you to do a small seed number of OTs and then extend them using only symmetric primitives. So we basically only need 200 basic OTs, and then we can extend these using just something like AES or SHA. So the downside of using OTE is that each call to this primitive basically requires either k bits or kappa bits, the minimum of those two right here. So for example, if we wanted to do 1024-bit multiplications right here, if these numbers are 1024, then the product is going to basically be, so essentially we then need to do, so k right here is basically going to be 1024. It's actually going to be 2048 if we want to keep the answer. If we want to keep the answer, we're going to have to do 2048. But forget that point right here. Whereas kappa, the symmetric key security primitive with something like AES, is simply something like 128 bits. So in other words, to do very large multiplications with this type of technique, we unfortunately have to use these OT strings have to be very big if you just use them as Gilboa basically states. So now you can sort of see where the first sort of real nice idea happens. So just to put that into perspective, essentially we need KOTs of size k bits, and so that's roughly k squared bits of communication per multiplication, and for one k-bit multiplication here. So here's our first big idea or small idea. It's just that if you want to do a multiplication in this ring, you can also do several multiplications in these smaller rings. And so just as a, if you follow along, what's the right size to set this particular parameter? How big should this Ni be? What? Yeah, roughly 128 bits here. Okay, and so if we basically want to do a multiplication like this, we can just do smaller multiplications like this. This does not help you in the plain text model. It's not like an improvement like Karatsuba or anything like this. This only helps because we're doing secure computation multiplications. So as Riyadh said, this should basically be 128 bits. Okay, so then T should be roughly K over kappa bits. Okay, and so then we basically need to do T multiplications, each of size, we need to do T multiplications, each of which are like kappa squared bits of communication. And so since T is K over kappa, we basically get k over kappa bits of communication. And so we basically saved a factor of like over k squared. We've saved a factor of k over kappa. Okay, so in this case, k is like 2048 and kappa is 128. So there we go. We've saved a factor of 16 there, and that's why this approach wins. But it gets better. It's not only this. Candidate trial division. So all proper approaches here, what they want to do is before spending the effort of multiplying a very large modulus with another very large modulus, we want to basically quickly sieve out the multiples of 3, 5, 7, 11, 13, etc. All the small primes we want to do some sort of trial division for. Okay? And now how do our previous approaches basically do this? So this paper right here, they use pi-a encryption. And so what they do is they basically take their number mod, let's say the small prime, encrypt it, and then send it out to everybody. They add all of them together. They multiply that by a random number, and then open that random number. Now what should the answer be if the number is not a multiple of 3, let's say? It should be random, right? Because I've taken a non-zero value and multiplied it by a random number, so I haven't really broken security. I've basically opened a random number. If, in fact, this number was, this distributed additive share was divisible by 3, then you know, when we sum up all of our residues mod 3, you would get something 0, and you multiply that by a random number, you get 0. You open the 0, and you know that your prime is basically broken. Now, the unfortunate thing is that requires 1 encryption, okay, and decryption per prime. And that needs to be communicated. Okay, so think about that communication. Flop, they use something better. They use 1 out of k OT. Okay, and so this is kind of how they do it. Their paper is in the two-party model. And so again, another question is how they extend it to multi-parties. It's not exactly clear, but one could do that. That wouldn't be the bottleneck. But there's no reason to, so let me explain. So P is basically P1 plus P2, and let's say we want to check divisibility by 7. What they also use, and the magic sauce of making these things efficient, is to try to use OT extension when you can because of AES. And so Alice is going to compute her residue mod 7. Bob is going to pick his residue mod 7. And Bob is going to know here, let's call these inputs 0, 1, 2, 3, 4, 5, and 6. So let's just say Bob's residue was 4. Okay? So Bob would know that if Alice's residue was 3, that would be bad. Okay? So he's going to put a bad string there, and he's going to put good strings everywhere else. And now the protocol is basically Alice does a 1 out of KOT on her residue. And if she recovers bad, she sends it back to Bob and say, this is bad. If it's good, well, all she's learned is that it's good, hasn't learned anything else about what Bob's residue was, and sends that back, does some sort of confirmation that that was a good thing. So the problem with this is 1 out of KOT basically requires k times kappa bits of communication. Okay, so that's one problem. The other problem is just the structure of this. So their trial division is going to work something like this. They're going to pick some share of P. They're going to do 1 out of 3 OT, a 1 out of 5 OT, a 1 out of 7 OT, 1 out of 11 OT, and then 1 out of, let's say the largest prime is 1,000, something roughly like that. They're going to do all of those OTs. And then if they all succeed, then the candidate can basically go ahead in time. The problem is, okay, let's say, for example, your first one succeeds, your second one succeeds, your third one succeeds, and now your fourth one basically fails right here. So this means essentially all of the work that you've basically done in vetting this prime, this one big P that you've chosen for this particular approach, all of the work that you've done to that particular point is basically tossed away. And question?
How does this work under adversarial conditions?
You mean under a malicious adversary?
Yeah.
So I'm going to talk. So
Okay,
this whole is basically about semi-honest approaches, and yes, one can basically get around these type of. So we have a strategy for malicious, but I don't want to get into that. It's kind of a more complicated thing. Yeah, the point is just work saving in the semi-honest case. That's what we're talking about here. And in this case, the observation is that when you pick your prime and start testing on that P, okay, you could end up wasting a lot of intermediate work. Now, of course, these intermediate stops right here, like 1 out of 47, let's say, right? That's going to succeed with 46 out of 47% of the chance, right? But on that roughly 2% of the leftover, you're wasting all of that previous work. So you kind of see how this work basically adds up in this 1 plus 2 plus 3 plus etc. kind of way. A better approach is again to think about. So again, this was the destructive thing. Pick a P and tear it down. Instead, another approach is a constructive approach. So the idea is that in fact you know that you need something that is a large number that is a non-zero residue mod 3. So we can basically toss some coins and pick something mod 3 and test mod 3, right? So we could go through some process to pick just some number in Z3 that is a non-zero sum mod 3. Right? So this is some process, and it's going to do a lot of work because, for example, 1/3 of the times that we do this, it's going to fail, right? But in any case, whatever succeeds, we basically put into our piggy bank right here. And then we have a slightly smaller process for 5. We put that into our piggy bank, and a slightly smaller process for 7, and a really small process for the piggy bank that's 1031. So let's construct these numbers separately, and then use our CRT representation. So if we want to basically get a number right here, we just extract one candidate from each of these particular piggy banks, and now we have a P. Okay? And so now there's basically no wasted tests. So if you recall over here, right, 1/3 of the tests are going to fail just on that first level, right? But a lot of the work that you do here is going to fail because you failed on the second level, or the third level, or the fourth level, or the fifth level, etc. All of that the tail weight of wasted work, basically we avoid. So that's why it's better to do constructive type of sieving like this. Okay? And now, if you put the first thing I said with the second thing I said, so here we are using the CRT, but let's apply the CRT again. So if we want to find a prime mod 3, what are we going to have to be using? OT extensions. And OT extensions are not very efficient with small primes. So we should do some sort of extra packing. And so instead of using the small primes, we should again use these small these ends, which are basically small products of primes. We should basically pick residues that are like pick numbers that are non-zero, like that are not smooth in N1, in N2, N3, etc., and then pull them all together. And one can basically write a small, you can try to be optimal here, but you could also just take a shortcut and make a greedy algorithm that tries to balance these things. And so these are basically the small ends. You see 3 kind of what you want to put with a bunch of larger ones, and 19 you can sort of like balance some of the smaller particular values here. So there are 9 candidates right here. And I'm almost done with this first set right here. The last observation I want to make is that in order to pick a number that's not 0, mod these N1s here, generally the approach, just like this PyA encryption, has been select a random PI, okay, we share it, then we select a random R and multiply the two together, and then open it, just like we did with the PyA thing. If it's 0, mod any of the small primes, because now we're working in N1, which is a product of small primes, then reject that number and throw it away, okay? If it's good, keep that P right there. Then do the same thing with Q. Pick a Q, pick another random R, open it, and see if it works. And if it is, now we have a P and a Q, we can multiply the P and Q. So there's an obvious optimization right here that we don't need the R right here and the other random R right here. The better approach is to select a random P, select a random Q. Since we have to multiply them anyway, multiply them. And since we're going to reveal N anyway, go ahead and reveal them. And if it's 0, then you basically exclude that slot. Otherwise, you keep that slot. Did that make sense? Right? So we basically get rid of that approach right there. So all in all, I told you we basically picked 9 of these type of things. And remember, we're going to basically, the algorithm, what we're going to do is this is going to be the first piggy bank. We're going to basically, this defines a ring based on these primes right here. We're going to basically randomly sample in this one until we get non-zero values. Then we're going to randomly sample here, here, and here. In fact, we're going to do them all in parallel. And we're going to fill our piggy banks with enough candidates. Okay? Some of these things are going to take more iterations than others. But we're going to fill each piggy bank with, let's say, 50 candidates. And then we're going to extract them and take that first prime, and et cetera. In fact, in this case, we're going to actually be able to extract the first n. Okay? And so all in all, we do the analysis. The number of f-mults, and these are optimal 128-bit OT extension-based multiplications, to produce a candidate P and Q is basically 14. Okay? And so far, what we've done, we've taken P's and Q's, and we've actually also produced the prefix of a product, okay, of P and Q. So we've used our multiplications sort of in two reasons. One, to test for divisibility by small primes, and we've used the multiplicate, we've sort of given it double duty. We've also used it to compute the eventual final product.
For 1024 or 2048?
14 for, this is for 1024. For two 1024 numbers that multiply to a 2048 number. Yeah, so we still have to do a little bit more work. That's the next slide right here. Share extensions. So when we have a number that's like this big, and when we multiply it, of course, the product is going to be bigger. And in the CRT representation, we have to extend and make those numbers as well. I basically said, here's another set of primes that we basically do that with. And so the overall work right here is we basically do 14 operations for this, 9 operations for here. This is 9 instead of 8, because in fact we also check for divisibility by this set of primes, and that actually helps us a little bit. And so the expected number of multiplications we needed to do produce a candidate that is a okay, sorry, there's one extra step right here. After we do this sieving, there's an 82% chance that the number is a prime, and so this second set of sieving, of course, gets rid of a few candidates, and so overall, I think, yeah, this is.
The second sieving is on the public end.
We haven't computed the public n yet. We've only computed the first half, mod the small ring. So what I wanted to skip over is this step right here. We take our original shares, extend them, like locally extend them, locally reconstruct them, and then take the modulo the second set of primes, and then do multiplications on those. Now, if something fails in those, we basically have to throw the whole thing away, okay? But and that happens with this 82%. So overall, this is the number I wanted to get to. It takes 14 numbers to produce a candidate. Then it takes, once we have that, we know that these numbers are not divisible by the first 131 primes. That's pretty good right there. Then we multiply them again, and some fraction of them pass. And so if you combine all three of these, essentially we need 27.5 expected number of f-mults to produce a candidate n. And this is an n that has been sieved already. And so, right, now that it's public, we can also locally start trying the first million primes. The point is we've already invested all of this work there. So doing all of that basically saves the work of biprimality testing. And that actually turns out, your protocol turns out to be, even though people complain about how you have to do this many repetitions, it turns out to be not the bottleneck of this at all. And so let me just get into that right there. This will just be the last slide, the last few slides. So our protocol basically consists of f mod gen, which together does all of those things, which is sieving and candidate generation, and then biprime, which is roughly the same idea that you had there. And mod gen only relies on f mul. That's our optimal multiplier. And f prime basically relies on two things. This is the sort of group multiplier that's pretty cheap. So in terms of deployability and sort of like part of this is to build something that's really easy to understand and also like easy to audit. And we only basically require one cryptographic primitive that requires a lot of care to look at. The rest of it is all gluing together. And now here's some performance numbers. We don't have all of the parts glued together because we're still optimizing certain parts of this. But we did take the current protocol I just did, and we express them in terms of these operations to get a sense of how much time it would actually take. And so we ran like 500 runs, and we basically, for each run, each run basically says how much, it runs until it actually outputs a value that succeeds. And we counted how many modgen operations we basically need. And that red line is basically the average. And I think this is somewhere in the 3,500. So we basically have to generate about 3,500 candidates. That lines up on average. That lines up perfectly with our analytical analysis. When we do all of the sieving analysis, we get a prime with roughly 1/60. And so doing that twice is roughly 1/3600. This is where the DM approach, this is the open problem, the DM approach. If we could basically sieve one prime and then another prime, multiply them together, then of course we'd only have to do about 120 of these modgen operations. So that's where I said there's a factor of 20 improvement. We suffer from this square problem of square and square. And there are some approaches, that like simple approaches to try to get around it. But just in the simple version.
So what's the ratio then between DM and this?
Well, DM, if you can basically, so here, again, the problem is we require the mutual coincidence of once that both of these things are prime, so we get squared. If we could do some sort of prime, if we could basically, like, here's one putative thing that doesn't exactly work. Maybe put 10 moduli together, okay, 10 of these like shots. And then if there are 10 choose 2 ways for us to win now, because if any 2 win, the whole modulus is secure. Possibly we could use that whole modulus in a DM approach to check the primality of each candidate. That approach doesn't work out for what I explained there, but it's not clear. That would be the right way, because then we basically do one big multiplication and then get a any choose 2 type of operation to help us win. But even this right here, I think, is in the land of feasible. Let me show you. So mod gen is this many. Bi prime is this many. I think the average was around 1180 number of operations. But again, this is not the bottleneck by any means. Gmul was that other thing. Here is the real fmul. Fmul is the OT extension. This characterizes how much work, essentially, ignoring fmul and those gmul and those other things, how much work each party has to do. And here you can sort of see the average, which is roughly around 75,000. So this is the number of OT extensions that each, so this is the number of calls to fmul. And if you think about n parties, each party has to do basically a counter, has to do an OT extension on each of these fmuls. So this is roughly the amount of work that each party has to do. 75,000 OT extensions. That's highly, highly feasible.
75,000 times 128.
Yeah.
Each F multi is 128 OT.
You're counting number of bits of communication. I'm saying.
No, number of OT. Each F multi requires 128.
Yes, sorry. You're right. Times 128.
How much runtime and how many bits of communication in actual numbers? Do you have estimate?
Well, I mean, aside from multiplying this out, so we haven't. So these are again just simulations right here. This is like a. So I haven't measured the network communication yet. This is just.
What's the ballpark estimate on the other?
Right. So I'll do it right now. 75,000 is let's just call that 100,000, right? So that's like 2 to the 17, okay? And we have to do 2 to the 7 OTs, okay? And each OT is 2 to the 7. So that's 14 plus 17, which is 2 to the 31 bits of communication. So that's less than 4 gigabytes, right? Per party.
And so is this number times n, like in the case of n parties?
Yeah.
How does it scale with respect to n?
Well, times n.
Times n. Everyone's, the total communication is.
This is.
Everyone's communication is.
This is the number of fmul operations, and each fmul operation requires each party to do that much communication per extra party. So it's like, let's say it's okay. So for 1,000 parties, it would basically, this is bits. So if we do this by, if we divide again into bytes, this is 2 to the 28 bytes per party. So what is that? That's 2 to the 30 is a billion. So this is 256 megabytes per party. So all right, if you multiply by 1,000, we're in the era of 256 gigabytes. So So that's a lot of communication, but that's not like if we're using Cloudflare, that's not like Google measures it in petabytes per day. So this is feasible.
But if you use LWE, it can go much shorter, maybe megabytes.
You have to do this in order to prove why LWE is so good, right?
Yes.
So I'm taking one for the team.
That is probably a threshold where
Yeah, of course.
number of parties
Yeah.
versus
So
which
in
of
100
these
parties, like if divide that by 100, and now it's 2 gigabytes per person for 120, 30 parties. And well, I'll give you a better sense of it, right? This is, how bad is 1 mult? This is Apple trying to help me here. So this is a 256 bit multiplication. So 250, it's 2 of them actually, because this is a pristine like run from our, so this is the amount of time with extra stuff being added. So this is an upper bound on what it takes for 256 bit multiplication without any of our optimizations and so forth. So it's roughly 300 milliseconds. And
I should correct myself. When I said megabytes, I was assuming a central coordinator which helps. Otherwise, asymptotically, if you look at the complexity, it's roughly the same.
right, you cannot get by this n squared business if you want n minus 1.
You can just improve with broadcasts, like if you use threshold data. That's the only advantage.
Okay, so all I'm hoping is I left you with an optimistic feeling for how this might work and a few problems that.
Maybe I'll make one comment in that I think it would be good if the modulus that's being generated doesn't have so 5n is not divisible by small prime factors.
So we're checking that P and Q are both 3 mod 4. Is that not
3
sufficient?
mod 4 is fine, but you would also like it to be not 0 mod 5, not 0 mod 7. I think these methods could actually guarantee that too.
This is for your strong? No.
No, so this wouldn't be strong, but it's sufficient.
What do you have to do for that? How do you check that?
Well, as you do your CRT, as you do your sieving, you wouldn't just check that it's not 0 mod 5. Sorry, you wouldn't just check that it's not 0 mod 5. You would check that it's also not minus 1 mod 5. And that would guarantee that P minus 1 is not divisible by 5.
Right.
Yeah. So I think it's just one more check.
Right.
And basically, for the same price, you could also guarantee there are no small prime factors.
Yes.
And that's really beneficial to these protocols.
Yes.
Yeah. So.
Yeah, well, as you said, it just comes for free, right?
Yeah.
Like when you open them, you just make sure in each slot that it's.
You're avoiding 0 mod 5.
Yeah, you can just avoid 0 and minus 1.
Should each prime be that way or the product?
No, each P and Q should be that way.
Because you're multiplying, so you will have to.
No, each prime. You just want to make sure none of the primes are 1 mod 5 and none of the primes are 0 mod 5. It's hard to be prime if you're 0 mod 5.
Right. Okay.
Yeah. So, but I think these methods actually.
So that would just increase the rejection rate. So it takes a little bit more work, but that's a good idea for us to look into that. And
Very nice.
what is the tangible benefit, though? Like, how does it get better when you have?
So right now we have to assume you can't find elements of order 3, whereas this would prove there are no elements of order 3.
Oh, is that? And you want to check for? How big do you want to check to?
Well, think of that.
Okay. I see.
Maybe I'm being a purist, but it would be nice. It's hard to find elements of order 3 mod n,
Yeah.
but it's even nicer to
Yes,
see
that they don't exist. Yeah.
You get it for free, so.
Yeah.
So I mean, as large as a prime that you want to also check the -1 mod value.